You send a transaction, it's clean, it's seamless, it just works. But then the system that felt so perfect just a moment ago starts to buckle under its own success. Blockchains were designed to scale for the entire world, so why do they fail the moment people actually start using them?
So at first, everything is perfect. You see that single transaction and bam, it confirms instantly. But then, then everyone else shows up. The network just gets flooded. We're talking hundreds, then thousands of transactions, all fighting for the same space. And that's when the system just starts to break. The network gets totally clogged, fees go through the roof, and everything just grinds to a halt. And this brings us to the absolute core question, really the whole point of this explainer. Why does a system that was designed for global scale break so easily? Why does success kill it? Let's get into it. But before we dive in, just a quick heads up. This explainer from Blockspawn's funds is created for educational and informational purposes only and does not constitute financial or investment advice. All right, so let's start with what I like to call the scaling paradox. It's this really weird thing where these incredible networks work flawlessly right up until they get popular. You know, for you, the end user, that first experience feels amazing. But what you don't see is that under the surface, with every single new person that joins, the strain is building up, just waiting to hit that tipping point. Now, for years, the go-to explanation for this whole paradox has been something you've probably heard of, the blockchain trilemma. It's basically become the default answer in the crypto space. This idea, which was really popularized by Ethereum co-founder Vitalik Buterin, suggests there's this fundamental trade-off. It says you can have 2 out of 3 things: decentralization, security, and scalability. You can have decentralized and secure, or you can have secure and scalable, but the trilemma says you can never ever have all 3 at once. Yeah, and this visual really nails it. Think of it like you're trying to balance this triangle. If you pull on one corner, let's say you try to crank up the scalability, you're automatically forced to give something up on another corner, like decentralization. And this is the exact choice that the big players, like Bitcoin and Ethereum, had to make. They went all in on decentralization and security. But what was the cost? Scalability. That's why their transaction speeds, their throughput, seem so incredibly low compared to something like Visa. Okay, but what if this whole framework, this trilemma that practically everyone accepts as gospel, what if it's actually flawed? What if it's not some law of the universe, but just a convenient story we've been telling ourselves? And this is where things get really interesting. We have to ask the hard question. Is the trilemma a real, unbreakable rule? Or is it just a mental model that's actually holding us back, making us believe in limits that maybe don't really exist? This leads us to a really powerful counterargument from a paper by Dr. Craig S. Wright. He argues that the trilemma isn't a law at all. He calls it a category error, basically a fundamental mistake in how we're classifying the problem. So what on earth is a category error? Well, think of it this way. It's like asking, which is heavier, the color blue or a musical note? The question makes no sense, right? You can't compare them because they belong to completely different categories. The argument here is that the same thing applies to the trilemma. Security is about logical rules, scalability is about raw computing power, and decentralization is about the physical layout of the network. They aren't 3 competing things on the same spectrum. They're describing totally different aspects of the system. Okay, so if the trilemma is a distraction, then what are the real roadblocks? Well, the answers are found in the messy physical world, the actual constraints that limit any big distributed system. The first real bottleneck? Just massive, mind-boggling inefficiency. In a system like Bitcoin or Ethereum, every single computer, every node on the network, has to do the exact same work. It has to process and validate every single transaction. It's security through repetition, but man, is it the polar opposite of efficient. The second bottleneck is just the laws of physics, pure and simple. Data doesn't just teleport. It takes real time for a new block of data to travel across the entire planet. This delay, what we call latency, puts a hard speed limit on the whole system.
And it gets way worse when the network is inefficiently blasting out that data, sending a separate individual copy to every single node one by one instead of broadcasting it smartly.
And this visual shows you exactly why that data travel time matters so much. For the entire system to be secure, every single participant has to be able to see the data and check it for themselves. But what happens if they can't even get their hands on the data in the first place?
And that question leads us directly to what might be the most critical bottleneck of all, the data availability problem. It boils down to this: how can any node be 100% sure that when a new block is announced, all the transaction data that's supposedly in it has actually been published and is available for anyone to check? Because if you can't guarantee that, the whole security model just falls apart. So once we started to really understand these real bottlenecks, the redundant work, the network delays, and this huge data availability problem, engineers could finally start building a new generation of solutions to tackle them head on. And right now, there are really three major strategies that are leading the charge: Layer 2 rollups, something called sharding, and a big picture idea called modular architecture. So first up, Layer 2 rollups. The basic idea is to move all the heavy lifting, all that computation, off the main, super congested blockchain. It's like building an express lane next to a traffic jam. They process thousands of transactions on the side, and then they just post a tiny compressed summary back to the main chain. Then you've got sharding. This tries to bring parallel processing to blockchain. So instead of one massive chain doing everything, you split the network into many smaller parallel chains, or shards, and each one handles its own little piece of the workload. Now, both of those ideas, rollups and sharding, they really fit into this bigger trend that's happening right now, which is modular architecture. The core concept is actually pretty simple. Instead of building one monolithic blockchain that tries to do everything, you break the system down into specialized jobs. You could have one layer that's amazing at executing transactions, a different layer that's only job is to finalize them, and another layer that does nothing but guaranteed data is available. It's all about specialization, letting each piece of the system get hyper-optimized for one specific thing.
So, where does all this leave us? We've kind of journeyed from this simple, maybe even misleading trilemma to a much more complex and honestly more realistic set of engineering challenges.
And this is the key takeaway. The ultimate speed limits on a blockchain aren't some abstract choice in a triangle. They are the hard, cold laws of our physical world. We're talking about bandwidth, the speed of light, which creates latency, and the sheer amount of computational power we can throw at the problem. And that really captures the heart of the problem, the ultimate challenge. This isn't just about making transactions go faster. It's about solving a monumental puzzle in distributed computing. How in the world do you get thousands of independent computers scattered all across the globe to coordinate so perfectly that they act like a single unified computer? Solving that is the real final frontier.